All right, and it's my great pleasure to introduce our last speaker in this session, although we will have a few words from our honoree at the end. And so I'd like to introduce John Ousterhout, who many of you know. He got his PhD at Carnegie Mellon. Of course, he's well known for work in a diverse set of fields, including the Magic and Caesar projects in VLSI, the Sprite operating system, Tickle TK. He's also well known for those of us who had the honor of being colleagues with him as somebody who not only trains great students, but also writes code himself in the projects. And that's something I'm kind of jealous of, but anyway, that I never feel like I have time to do that. And I think he's going to talk to us today about how you train really super programmers.
Great, thank you. And thanks for staying around, by the way. So after hearing the last talk, just to set your expectations right, what you're going to hear for the next 20 minutes is pretty much the opposite. So I guess Dave would say, this is going to be really small. So the title of this talk is a question I've been asking myself for a couple of decades about whether we can teach the skills of great programmers. And I've been wondering back and forth about it. And finally, a couple of years ago, I decided it's only one way to answer the question, and that's to give it a try. So I'm going to talk a little bit about a course that I taught once last year, and I'm teaching again for the second time now, where I try and teach the skills of great programmers. So first, a couple of things that motivated this course. The first one is a question. The question for you is, what's the most important idea in all of computer science? And if you think about what idea permeates every subfield of computer science, the most important thing, some people would say algorithms. No, that's actually not it. Very few people actually write algorithms once they get out of school. I asked Don Knuth, and he was able to guess an answer that was mostly right. He said layers of abstraction. I would say the answer is problem decomposition. How do you take a really big, complicated problem and break it up into pieces that you can solve relatively independently, so you can turn a very complex task into a bunch of relatively simple tasks? Well, the irony is, as far as I know, no one attempts to teach this in any of our classes, at least up until I tried a year ago. By the way, if you know of a class where one of the primary things in the class is to teach problem decomposition, come tell me about it. I'd like to learn more about the class and the techniques they use. So that's the first proposition. The second is, we know that there's this class of programmers that are just way, way, way better than average programmers. I think Google calls them 10x programmers, although there's some indications that it's more than an order of magnitude difference in their productivity. And yet, as far as I know, nobody tries to teach the skills that separate elite programmers from good programmers. And so I'm not talking about software engineering now. I'm talking about software design, the things that really make the great programmers. Again, if you know of a class that does this, come tell me about it. I'd love to learn about it. So I decided to set out and see if I could do this. Well, this naturally immediately raises three questions. The first one, is this even possible? Is great programming skill something that's innate at birth? Well, I read this great book a couple of summers ago called Talent is Overrated. And since then, I've seen more and more scientific evidence, and all of the scientific evidence is totally aligned that says, no, there's essentially no such thing as innate talent. There are some physical attributes like size and weight, perhaps, that are innate, but all of the things that we think of as great skills are learned, and the primary thing that separates great performers in any field from the average performers is how much they've practiced. That's the only real difference. So given that, I thought, okay, let's give this a try. Maybe it's possible to teach these skills. And the second thing is, well, who's going to do it? Since nobody learned it, so the only way to even know this is through personal experience. And of course, nobody that teaches actually writes any code. And so how would any of our teachers learn it? Well, fortunately, or I don't know, unfortunately, whatever, I'm one of those freaks who still writes code. I've written, I think, close to 300,000 lines of code in my career and a bunch of very large systems. And I've been thinking about these issues, so I figured, if anybody can do it, I've probably got about as good a shot as anybody. But probably there aren't very many people who could do it. And then the third question is, well, how do you do this, and what's the technique for this? So the technique I decided to use for the class is called CS190, Software Design Studio. The technique I use is more like an English writing class. When you learn to write, what you do is you write something, you give it to your teacher, he or she marks it up with red ink, you go back and you write it again, they mark it up again, and you repeat this process over and over and over again, and through that iteration process, you gradually learn how to write well. So I decided to try that approach in this class. Unfortunately, we're limited by the confines of a quarter to a relatively small number of iterations. But the way the class works is that we first start off, and in teams of 2, students undertake the largest possible project they can reasonably do in 3 weeks of the course. This year, it was a graphical text editor with multiple windows and infinite level undo redo. About 2,000 lines of code to implement that, roughly. So they do that. They get no hints about how to decompose the problem. They have to figure it out completely on their own. Then we do a round of code reviews, both in class, and also I read the code and I meet with all of the students. And then in the second phase, they go back and they revise their project to take into account all of the things they learned in the code reviews. We do another round of code reviews after that. And then for the third phase, I swap the projects. So every team gets some other team's project. They all were building the same thing, but they get somebody else's team project, and then they have to add new features onto that. And along the way, they're expected to refactor, to identify problems in that project and fix problems as well as adding new features. And then finally, we do a third round of code reviews after all of that. So they get 3 rounds over the course of a quarter. Now, unfortunately, this is not a scalable approach. It's the opposite of a MOOC. We can't handle more than about 20 students in the class. And the problem is, I read every line of code that every team writes. So in week 4 of the class, I typically have to read 15 to 20,000 lines of code and do code reviews on it. I give typically 50 to 100 comments on each project. I spend about an hour meeting with the teams later to go over all of that, and then I repeat that twice more. And I don't think I can use TAs for this yet because, again, I haven't been able to codify the class enough that I think somebody else could figure out how to grade the assignment. So it's an extremely labor-intensive class to do. But now you're probably wondering, well, but what are the secrets? So what do you do to be a great programmer? What do you do to be a great programmer? And by the way, what makes you think you know what the secrets are? So I'll try the second question first. The answer is I don't. I've been thinking about this for a long time as I've been writing code, so I've been trying to think about it, but the answer to that second question, I say, is it's a little bit of hubris and a little bit of hope. And I guess I'd like to think that maybe I have a few ideas. But what are the secrets? So I've listed a few of the key ideas in the class on this slide here, but you're going to look at them and say, those are pretty vague. How can those possibly be actionable in actually writing code? There's not a lot of lecture in the class. There's only about 6 or 7 lectures at the beginning of the class, and then after that, it's really all about students writing code and then using the code that they've written and the errors they make to illustrate these issues. And I do have actually some more sort of concrete techniques that are part of these issues here. But honestly, it only works in the context of looking over their code. And I will say that I think the course is more about, as I said on the slide, more about red flags than recipes. That is, I think I can tell students how they can identify code that's pretty good and code that's not so good. It's much harder to say how to get from the bad code to the good code. I have some ideas about that, but I would say that's less well-formed. On the other hand, I think if you give a smart person a good set of red flags, if they know they're doing it wrong and they have a reasonable attention span, they can eventually find their way to the right answer. So what I thought I would do is just pick 2 of these examples and talk through them in a little bit more detail to give you a sense of the kind of things that I talk about. So the first one is the notion, by the way, these are both things that I think the students find a little bit surprising because they go against things they may have been taught in other classes or heard in their internships. So the first one is the notion that classes should be thick. So what do I mean by that? Well, if you think of a class as this big wad of code here, a class has really 2 things. It has some functionality that it implements, and then it has, at the edge of that, there's this interface which is everything that anybody would need to know in order to use that class. It's not just the method signatures, but potentially other information about side effects and exceptions and subtleties like that. So when I say classes should be thick, what I mean is that we want to have as small as possible an interface to as large as possible an amount of functionality in that class. And the reason is that the main thing we're trying to deal with in software design is we're trying to manage complexity. That's the fundamental goal, is to somehow make a complicated system seem simple. And so what we want to do is take a thing that's relatively complicated, that implementation, and provide a relatively simple way of thinking about that complicated thing. Of course, that's abstraction. That's the whole idea behind abstraction. And this is really just a reformulation of the ideas from the classic David Parnas paper from about 1970 titled On the Criteria to be Used in Decomposing Systems into Modules. which, by the way, to me, this is one of the two most important papers in all of software design. By the way, how many people here have read that paper? Not enough. All right, well, if you want to be a software designer someday when you grow up, I'd go read that paper. So a thin class is a class that has a really big interface and not much implementation. So my canonical example of a thin class is a linked list module. Honestly, you can practically just do the linked list operations in about the same amount of code as you could call a method to do it for you. So there's very little abstraction there, and therefore, you get very little leverage against complexity. You haven't really reduced the overall complexity problem very much. Sometimes we have to have thin classes, but they don't buy you much. A thick class, on the other hand, has a really, really thin, very, very small interface to a huge amount of functionality underneath. An example of this is not so much a class, but a module in Unix, the I/O system. You have 4 kernel calls: read, write, open, and close. Incredibly simple interface, and an enormous amount of functionality underneath that in terms of managing disks and I/O devices and taking interrupts and so on. That's all hidden underneath that. So that's an example of a very thick interface or module. Here's another example of a typical thin method. This was one taken from one of the students' assignments this quarter. A private is a very thin method. A private method in a class. The name is add null value for attribute, and then you can see that line, data.put attribute null. It would actually be fewer characters. Rather than typing that function name, it would be fewer characters to just type that line, data.put attribute comma null. And I see this a lot. So unfortunately, the common wisdom, what people are taught in classes, is that classes and methods should be short as opposed to thick. And that leads to a disease that I call classitis. Classitis is an illness that happens when somebody says classes are good, and somebody else thought what they said was more classes are better. And so the result of that is you make as many classes as you possibly can, each one adding as little functionality as possible. This is a mantra of the Java world. Java has rampant classitis, where it seems like the idea is never create one class when 2 classes or 3 classes will do. Each class should add the least possible amount of functionality to all the classes that went before. And maybe one of my most hated pieces of code in the world is what it takes to actually open a file for I/O in Java. If you want to read serialized objects from a file, you have to create 3 different objects of different classes. One for the basic file stream, and then if you want buffering, what do you mean if I want buffering? Duh. Why are you even asking me this question? You have to create a whole separate class. You forget to do that, you get slow I/O. And then on top of that, then you create another class to do the object stream. So this is just sort of crazy, exposing people to all of these interfaces with almost no functionality underneath them. So again, length isn't so much the issue, it's abstraction. You need classes that abstract. We have simple interfaces hiding a lot of complexity. All right, that's the first one. Second idea from the class is define errors out of existence. So exceptions are an enormous source of complexity in applications. They're one of the biggest, I think, sources of complexity in applications today. And the common wisdom that people are taught is you should program defensively, and what that means is to detect as many problems or possible problems as possible and throw errors or exceptions for all of them. And as long as you detect a problem and throw an exception and document that, you don't have to worry about the impact of that exception on the caller. That's their problem. You've done your job. So what I would argue is, no, it's better if, whenever you possibly can, define your system such that there simply is no error, that all of the semantics actually are well defined. Let me give you a couple of examples of this. So one of the biggest mistakes I've made in my career was the design of the unset command in Tcl. Unset's a command that takes a variable name and deletes that variable. And I thought when I was building Tcl, I thought, no one would ever delete a variable that doesn't already exist. That's sort of stupid. It's an error. I should throw an exception for that. And so defined the command that way. This command has just been the source of so much hassle. Probably it's the largest single thing that people would complain about on the Tcl mailing list, because you'd end up in these situations where you've done some work, you may or may not have created variables, and you just want to clean up after yourself. You just want to make those variables go away. Then you end up every unset command ends up being captured in a catch that would catch the exception that might come from that and throw that away. It'd be so much simpler. It would have been so much better just to define the semantics of the command. The semantics are, make it so this variable no longer exists. If the variable already doesn't exist, you're done. It's fine. Just do nothing. Return silently. That would have been so much better. Of course, my second mistake was not to just bite the bullet and change it, but I was worried that somehow there'd be enough people out there that depended on the existing behavior that I didn't dare change it, but that's a different problem. Another example is in the Windows world. This has changed over time, but originally in Windows, if you tried to delete a file that was open, I assume the Windows developer thought, why would anybody delete a file that's open? That's a mistake. It would not let you do it. And so you often end up in the situation where you're trying to delete a file, would say, sorry, can't delete file, it's open. Then you have to go around and try and figure out which process in the system could possibly have this file open and kill it. And you just go around starting killing processes and trying the command over and over again until you can eventually delete the file. Unix has such a beautiful solution to this problem. In so many ways, Unix has so many beautiful solutions. In Unix, if you delete a file, it deletes the name for the file, so the directory is now empty. But the file itself stays around as long as it's open, so you can continue to use it. And then once you close the file, then the representation on disk finally does get deleted. But Windows didn't do it that way, but they found out about the problem. And so then they eventually changed it so you could actually delete a file that was open. But then they left the directory entry around, and you couldn't create a new file in the same place until the file got deleted. So a common paradigm where you remove a file and put a new one in its place still didn't work. So again, these are both examples where you just define the error out of existence. And I say overall, the goal in error handling is to try and somehow minimize the number of places where somebody has to worry about an exception. The only good exception is one that doesn't ever happen and you don't have to worry about. But people don't tend to think that way. Again, they tend to think more exceptions are better. I'm a better programmer if I threw more exceptions. So just a couple of examples. So just to close up, is the course working? Honestly, there's no way to tell right now. Clearly, students are not going to become 10x programmers in one quarter. Like all other great skills, it probably takes 5 to 10 years of practice with a lot of repetition over a long period of time to really master the skills. So I guess we'll have to ask them in some time in the future. I'd like to think it's the first step to try and get people thinking about complexity as a design issue and what that means and what kinds of things are more complicated or less complicated. The class itself has great energy, students super engaged. The thing I noticed last year was about halfway through the course there was a sudden change in the tenor of the discussions in class. In the first code review, students were very tentative, kind of a little uncomfortable, criticizing each other and not really sure what to talk about or how to think about it. But after they got unloaded on by me and had a chance to talk about that, they got kind of a better feel for it. Then suddenly the conversations all of a sudden changed in the middle of the second code review, where we had really great discussions about why this particular feature might or might not increase the complexity of the system. So that was a good sign. And the students seemed to really enjoy it, and I got some of the highest teaching ratings I've ever gotten from the class. But it's too soon to tell. However, I will say the class has been really interesting for me. It's just been a fun challenge to think about the material and try and think about what does cause complexity. I mean, I've been thinking about this off and on over my career, but now I have a really focused chance to see it, and I see 5 or 10 teams implement the same thing, the same project, and get different results, but you can start seeing trends among those, how they all make the same kind of mistakes. And so I'm starting to get more and more ideas for how you can think about code and how you can design really, really simple code. One example of that, I had this sudden realization this quarter, for some reason, I didn't see it last year, that making classes generic rather than specialized cuts the complexity tremendously. You might think that somehow specializing makes it simpler, you can do just what the application needs, avoid a lot of extra stuff. It's just not true at all. Specialization makes classes really complicated. I've been programming about 40 years now. Somehow that thought had never occurred to me until I saw this year every project over-specialized their class, like they combined the undo and the text modules together in various funky ways. And in every case, it made the code really, really complicated. So I can't say yet whether the students are learning how to be a great programmer, but I can say I think I'm actually getting to be a better programmer from the class. And I'm having a lot of fun. So with that, I'll stop and take questions.
Who's up? Am I up? All right. Fred Douglas, EMC, and one of John's PhDs. So When is the right time for students to take this class? You talked about unlearning bad habits, but they need to learn enough programming to be comfortable doing all this.
Yeah, good question. My goal is for them to take it as late as possible. I want them to have seen as much code as possible. I require them to have taken our operating system course in which they have to look at a pretty big system and work inside it, so that there's some hope that they can kind of understand why the principles matter in the class. So later's better.
Luigi from Google. Your talk started with the assumption that there are these 10x programmers. How do you define a 10x programmer? Is it effectiveness? Is it quality of code? And how can you make that measure somehow objective?
Yeah, honestly, I have no idea. We tend to recognize them. Typically, it's not hard to agree on most of these people, but you're right, we don't have good objective metrics. So I heard one good metric, which was from Alan Eustace at Google. And Alan said they use a metric where they ask the question, take our very best programmer. Suppose we had a choice. Either we could lose that programmer, or we could lose our n worst programmers. It's either worst or average, I don't remember which one. But n other programmers, how big is n when that balances? And he said at Google, the answer is about 300.
John, since many of us code by cloning from GitHub or by copying and pasting from Stack Overflow, what did you learn from the last part of the project? Any lessons? What happens when I start using somebody else's code and try to?
What did they learn when they had to work with somebody else's code? You know, I'm not sure I can think of a specific thing. I asked the students afterwards how they felt about it, and they said that was actually one of the best parts of the course for them. I think the main thing is that it really forces you to understand somebody else's code. And so one of the ways you learn is by comparing different codes. So I think the combination of the code reviews and the swap forces people to see the same thing implemented many different ways. And so I hope that helps to expose them. By the way, while we're, just a quick break in the question, I'd like to see a show of hands about how you feel about whether great programmers can be taught. So how many of you think that great programming is actually a teachable skill versus innate?
Why not?
How many think it's more innate, can't be taught? By the way, Don Knuth voted for innate also. I was kind of surprised.
So I have a question, a nomination, and a request. So the question, which a lot of people shouted out as you mentioned.
Sorry, where are you? Can you stand up?
I'm right here. It's Rick. Hi, John.
Oh, hi.
So the question, which a lot of people shouted out when you mentioned the Parnas paper, is what was the other really important paper on software design? I have a nomination, which is probably not yours, but it's the Tickle TK Engineering Manual. And the request is, please update that paper with the material in this talk.
So it's not the Tickle TK Engineering Manual. It's the Unix time-sharing system. Unix is in my opinion, is the most beautiful, sensationally magical piece of software ever designed in terms of finding, if you think about what you're trying to do, is find this very simple way to deal with very complex things. In my view, there's never been a software system like the early versions of Unix. So that's the sort of the standard to which I aspire. Dave?
Request? Rewrite your book?
I'm probably not going to edit that. I am thinking of trying to write a series of articles on the ideas from the course to try and write down the kinds of things I'm teaching.
Yeah, that was the thing that struck me, is it seems like you don't know if it's working. It will probably take a long time to figure out it's working. But it seems like you're forming strong opinions about what good code looks like. So it seems like you could write a book. Yeah, even though, because this, you're pretty sure what the good advice, or there's some good advice you're discovering, even though you don't know if you can so even if you can't teach people when they're undergraduates to become great programmers, it seems like you're capturing advice that would be useful for a lot of people.
I can articulate a heartfelt opinion.
Well,
yeah, and I think I will try and do that. I don't know if a book or a series of shorter essays, but I think
I think the thing that struck me when I gave that talk yesterday, I was, you're trying to figure out what to pass on, and I was trying to come up with what books could I get people to read? And I realized the longer the book, the less likely people would read it. So I think, the Strunk and White or 1 Minute Manager, 100-page book, so I think if you shot for 100 pages, on how to become a better programmer, or, and with these advice, and I think you've got examples you can show people now, assuming you can get permission to use the code. So I think that's doable. And if you keep it 100 pages, A, it takes a lot less time to write it, and B, a lot more people will read it. So.
Great advice. Have you ever thought about giving advice to people?
Yeah.
You seem to do that really well.
Hi, this is Ofer from Google, and formerly your neighbor from Gates' third floor. At Google, there is a class that does something similar to that, where people sit down for half a day and program in pairs smaller exercises of 45 minutes and then do code reviews to each other and between the groups. So pretty much the same thing, but much faster iteration. Have you given any thought to, is it the count of iterations that counts? Is it the size of the project? Could you do 10 iterations in 10 weeks?
Yeah, that's an interesting question. Next week, I'm going to try a slightly different exercise in class where I give people a problem in class and have them divide up into groups and just write the API with no code other than the API. And we'll probably spend 2 or 3 class periods doing that and then talking about that. I'll be curious to see how that works. You know, the problem is there's this trade-off between scale and complexity. And so can you really look at big complexity issues at small scale? Even the project we have is still borderline, too small for complexity. But we'll try some stuff like that and see if it works.
John Massey here. You mentioned Unix, right? And of course, I learned it from looking at the code because that's all we had in 1973. But that's an illustration, though, of the difficulty. I can't imagine how to train somebody to be Ken Thompson. Okay, all right. And the trouble is, for instance, there's a great paper that I think he never published, I found on his machine, when he talked about features that filled much needed gaps. And that shows up here. Anyway, I think realistically, I used to teach software project management and engineering at Bell Labs, and there clearly were some innate differences, but people could certainly learn to do better. But they were a lot of these same methods that you used, in terms of code reviews and people looking at stuff and looking at good examples. I mean, a lot of people learned Unix because they looked at good code.
Yeah, being able to write Unix is sort of the holy grail. If there's some way I could somehow give people a few hints that they could, over their careers, develop skills to do that. You're right, that's hard. There's probably only one Ken Thompson in the world. But I still feel like we have a shot.
Great. Well, thanks again.